Today, we are going to discuss about LCR series circuit. In this, we'll have an inductor, capacitor, and a resistance connected in series, and it is connected to AC source like this. Equation of this, if you use Kirchhoff law, will be L di by dt, which is potential difference across the inductor, plus I into R, which is potential difference across the resistance, and Q by C, which is potential difference across the capacitor, must be equal to source voltage V. Derivation of this is beyond our syllabus. So we use phasor method to solve this one. We don't use normal mathematics. First of all, let us calculate reactances. XL, inductive reactance. We know this formula already. XL is equal to omega L. Capacitive reactance. XC is equal to 1 by omega C. Once we got inductive and capacitive reactances, we calculate voltage across each circuit element. We know that in series combination current remains same. We can take that current as I. Now we calculate voltage across inductor. VL is equal to I into XL. Voltage across capacitor will be equal to I into XC. And voltage across resistance is equal to I into R. Now, we know in AC, in series combination, we add voltages like phasor or vectors. Let us make the phasor diagram. We can write voltage across resistance as VR, voltage across inductor VL, and voltage across capacitor as VC. We know that voltage across inductor will be 90 degrees in lead, and voltage across capacitor will be 90 degrees in lag. Now resultant voltage will be like this, and current will be in phase with resistance, voltage across resistance, and the phase angle is phi. This is voltage phasor. Now we need to add these voltages according to vector addition or phasor addition. So V bar is equal to VL plus VC plus VR, vector addition. We know that when we go through vector addition, these two are opposite to each other. Then the resultant will be VL minus VC in this direction, and I'm considering VL is greater than VC. Once I add VL and VC according to vector addition, VL minus VC will be like this, and VR will be like this. Resultant V will be like this. So magnitude of V can be written as VR square plus VL minus VC whole square under root. Now we substitute VR, VL, VC values from the above equations. Then V is equal to I into R whole square plus I into XL minus I into XC whole square under root. Now if I take I common, V is equal to I into square root of R square plus XL minus XC whole square. I is equal to V by this entire value. If you compare this with I is equal to V by Z, we can say Z is equal to R square plus XL minus XC whole square under root. It is clear that Z will play the role of resistance in DC circuit, and Z is called as impedance. Now we can write impedance triangle like this with same phase angle phi. This will be XL minus XC, and this is R, and the net value is Z. Now we calculate phase angle. From the triangle we can write tan phi is equal to XL minus XC by R, or cos phi is equal to R by Z. Now observe, entire this derivation is taken by considering VL is more than VC. If VC is more than VL, still the equation is valid. Reason is that although this term becomes negative, square becomes positive. So no need to worry about it, doesn't affect final result. But if XL is greater than XC, then it is called as inductive circuit. Because in this, inductance will be in dominance. Check it. You can say voltage across inductor will be more. If XC is greater than XL, then it is called as capacitive circuit. Just remember these 2 points required for CBSE. Now we discuss a special case in series LCR circuit called as resonance. Let us take series LCR circuit and let us take the impedance. Impedance is Z is equal to R square plus XL minus XC whole square. You know very well, as the frequency of source changes, XL, XC values will change, so impedance values will change. At a particular source frequency, impedance of the circuit will be minimum. Because impedance is minimum, current will be maximum. This condition is called as resonance, and this frequency is called as resonance frequency. So let us calculate minimum value of Z. Minimum value means R square plus XL minus XC whole square. It is obvious that the minimum value of this one can be 0. It cannot be negative because square is there. So if this is 0, XL minus XC must be equal to 0. XL equal to XC. Now let us substitute the value of XL XC in this. Then we'll get the answer that omega L is equal to 1 by omega C. Further, if you derive, then omega is equal to 1 by root LC. This is the resonance frequency. At this frequency, impedance Z will be equal to R and circuit is purely resistive. Now, let us understand this resonance with graph. Let us make a graph between source frequency omega and resistance and reactance, both inductive capacitor reactance, both on a y-axis. First, we take resistance. Resistance is independent of omega. It remains constant irrespective of omega. No problem. Next, let us go for inductive reactance. XL is equal to omega L. So it's in the form of y is equal to mx plus c, where c is 0. So it's a straight line passing through origin. It will be like this, XL. Now, XC, capacitive reactance, that is equal to 1 by omega c. On y-axis, we have XC. On x-axis, we have omega. So it is in the form of y is equal to 1 by x. It's a rectangular hyperbola like this. If you observe these two, at very low frequencies, resistance due to capacitor is very high. So in series circuit, the current is blocked by capacitor. Now, at very high frequencies, capacitive reactance is almost 0, but inductive reactance is very high. So inductor will block the current. But if you observe closely, at one particular frequency, both are allowing moderately or both are blocking moderately. That frequency is called as resonance frequency. At that point, XL is equal to XC. Below resonance frequency, capacitor is blocking, so it's a capacitive circuit. Above resonance frequency, inductor is blocking, so it is inductive circuit. Exactly at resonance, it is pure resistive circuit. Let us understand same concept through another graph. Source frequency versus current amplitude graph. Let us focus on this blue line. If you observe closely, you will understand that at very low frequencies, current is almost 0. At very high frequency also, current is nearly 0. As the frequency increases, the current will increase and increase. It goes to maximum value. Beyond that, it goes down further. This frequency is called as resonance frequency, where current is maximum and resistance or impedance is minimum. There is one more graph also. What is the difference between them? Both have same values of inductance and capacitance. Only thing is the resistance. The first graph has low resistance, second graph has high resistance. And observe in the left hand side, that means low frequency range, it is more and more capacitive circuit because capacitor is more active, resisting the current. And beyond this, that beyond resonance frequency is called as inductive circuit. There is one small thing called as quality factor, Q factor, which is not in the syllabus. Just remember the formula. Q factor is equal to omega naught L by R, or you can write 1 by omega naught CR. Just remember the formula, but this is not in the syllabus of NCERT.